In the previous videos, we discussed the gear fundamentals and design of spur gearing teeth. Now in this video, I shall discuss the design of shaft and gear blank and computer aided design. This slide shows the contents of this video. The pinion shaft loading is shown in figure 1. First consider the right hand side figure where the driver, that is the pinion, exerts a force Ft on the driven gear. The force Fr is also shown in position. To see the effect of Ft on the pinion shaft, draw two arrows as shown by red color acting in opposite directions at the center of the pinion. The arrow acting towards the right and force Ft are two parallel forces acting in opposite direction, and they constitute a couple which is nothing but torque acting on the shaft, and it is equal to Ft into dp by 2. The red arrow force acting in left direction causes the bending of the pinion shaft. For that, refer figure on the left where the force Ft is shown by a cross at the middle of the pinion. The pinion shaft is supported in the bearing and the overhang part of the shaft carries the pinion. The bending moment arm for force Ft is L, which is known as overhang. It is the distance between the central plane of the bearing housing to the central plane of the pinion. So the bending moment due to Ft is Mt is equal to Ft into overhang L. The force Fr is also shown in the left hand figure, and the bending moment due to Fr is Mr is equal to Fr into the overhang L. Overhang can be calculated from the equation which is given here, where basically D represents half of the bearing housing width and has been taken as equal to the shaft diameter. C dash is the clearance which is taken as 5 to 10 mm, and B by 2 is the half of the width of the pinion. The planes of above mentioned bending moments are perpendicular to each other. Hence, the resultant bending moment can be calculated from the equation given below, and equivalent torque from the equation given here, where Cm and Ct are termed as shock and fatigue factors. The required pinion shaft diameter is D is equal to cube root of 16T equivalent divided by pi tau, where tau is the allowable shear stress for the shaft material. Mild steel, approximately 0.2% carbon shafts are commonly used. The American Society of Mechanical Engineers Code recommends tau is equal to 40 MPa for commercial steel shafting with keyway. Using a similar approach, the gear shaft can be designed. In the previously presented video, Drive 4 Design of Gearing Spur Gears Part 3, two alternative designs of the spur gearing with significantly different number of teeth and diameters of pinion and gear were presented for the same power and speeds. It is to note that a gear with a larger diameter or larger number of teeth experiences smaller tooth load. Ft has been found to have much smaller value when the gear diameter is large, 2744 Newton versus 6174 Newton. Thus, for larger diameter gears, the bending load on the shaft and the load on the supporting bearings are lower. Though the larger diameter gears require more radial space and the cost of the gear blanks is high, the shaft and bearings costs are lower with large diameter gearing. Optimization considering these contradictory effects is desired. Now we take up an example of design of shaft. The gearing data obtained from the design based on the Lewis beam equation for type 1 problem are reproduced here. The pressure angle is 20 degree, the beam width 44 mm, the pinion diameter 80 mm, the gear diameter 280 mm, the pitch line velocity is 3.64 meter per second, and the tangential tooth load is 6174 Newton. Refer the discussion on design of shafts. From the force triangle shown in figure 2, the radial load Fr can be readily calculated as Ft 10 phi, that is 2247 Newton. The resultant bending moment can be calculated from the equation given. For a trial value of overhang L is equal to 100 mm. We have taken a trial value of overhang L because in the equation of L, the shaft diameter is not known to us. The torque for the gear shaft is Ft into dg by 2 and its value is given here. The gear shaft is subjected to a higher torque while the bending moment is the same for both the shafts. Hence, the gear shaft will have a larger diameter and is designed first. The equivalent torque can be calculated from the equation given here, where Cm and Ct are shock and fatigue factors to be taken from table 1. Since the series factor Cs, which takes account of the effect of the shock, has been considered to calculate Ft, the shock and fatigue factor considered here are Ct is equal to 1 and Cm is equal to 1.5, which is the minimum value as given in table 1. The required shaft diameter is calculated as 55 mm. Use a standard shaft diameter of 56 mm. For standard shaft diameter series, refer reference 1. The actual overhang comes out to be d plus b by 2 plus c dash, that is equal to 56 plus half of the beam width 22 plus clearance 10 mm, that is equal to 88 mm, while we considered it to be 100 mm for first trial. So redesign with overhang approximately equal to 90 mm, and this gives the revised shaft diameter as 53.8 mm, for which also the standard shaft diameter is 56 mm. For the pinion shaft, the torque is Ft into dp by 2 and its value is given here. The bending moment is the same as for the gear shaft and it is given here as 5.91 into 10 raised to power 5 Newton mm for overhang is equal to 90 mm. The equivalent torque can be calculated now, taking again Cm is equal to 1.5 and Ct is equal to 1, and this gives the required pinion shaft diameter as 48.8 mm, where tau is equal to 40 MPa. A 50 mm standard size shaft may be used. A square key of size dp by 4 into dp by 4, that is 13 mm into 13 mm, may be used. Now we discuss some aspects of gear blank design. Gear blanks are basically of three types. Very small diameter gear blanks are basically discs of uniform thickness. Small to medium diameter gears are wave type with handling holes. Refer figure 3 first. Large diameter gears are made with 3 to 12 arms depending on the diameter of the gear. Refer figure 3 The gear arms are designed in bending. The bending moment at section XX for all the arms is M is equal to Ft divided by Cv multiplied by pitch circle radius minus hub radius. The tangential tooth load Ft has been divided by Cv because the load is dynamic. And pitch circle radius minus hub radius is the arm for the bending moment. The required section modulus can be calculated from the equation given here, where M has been divided by I, that is number of arms. For the elliptical section of the arm as seen in the figure, Z arm is equal to pi by 32 A1 is square B1, where A1 is the major axis of the elliptical section of the arm and B1 is the minor axis. If A1 is twice the minor axis B1, then A1 is equal to 64 Z arm divided by pi whole power 1 by 3. Now I continue with the example which we have discussed earlier and take up the design of pinion and gear blanks. The pinion diameter dp is 80 mm only, hence the pinion blank would be simply a solid disc of addendum diameter, that is the pitch circle diameter dp plus 2 times of the addendum, and thickness will be equal to the tooth width thickness, that is 44 mm. The gear diameter is 280 mm, giving pitch circle radius of 140 mm. For the 56 mm diameter shaft, the hub diameter may be taken as 1.8 times the shaft diameter, that is say 100 mm. Hence the hub radius is 50 mm. The space between the rim and the hub would be less than pitch radius minus hub radius, that is less than 90 mm only. Refer figure 3 for clarity. Hence a wave type gear may be used with wave thickness of the order of 3 to 5 mm. For more details of minor nature, refer reference 1. The solution of a design problem may require trial and error, that is, the iteration may be involved. When a design requires a considerable amount of iteration or a particular machine element is frequently designed, a computer program is very useful. A computer is capable of executing a program at a very high speed. Hence, it is easy to develop alternative solutions which may be required for the optimization. A computer program is basically a sequence of instructions to be executed by a computer. In general, a design program may consist of a number of callable subroutines. Thus, the development of a program requires a lot of effort and skill. We have seen that the value of the pitch line velocity v and hence the velocity vector cv and tangential tooth load ft depend both on the number of teeth z and module m. The form factor y depends only on the number of teeth for a specified pressure angle. The solution of a problem is also governed by the constraint, if any, imposed. First, we consider the case where no constraint is imposed. In this case, the following solution procedure may be adopted. Select the service vector Cs and the pressure angle phi. Select material and specify the allowable stresses for pinion and gear materials, and assume B by M, say 10 to 11. Select value of number of teeth for the pinion to avoid interference. Begin with the lowest value of the module M, say M is equal to 0.25 mm. Calculate the diameter of the pinion and gear. Calculate the velocity factor, the form factors for pinion and gear, and the beam width B, which is equal to B1 multiplied by the module. Next, calculate the value of the right hand side of Levy's beam equation, which is basically the beam strength of the tooth. It may be denoted as Ft1. Calculate tangential tooth load Ft. If the beam strength Ft1 is greater than or equal to the load Ft, the module is decided. If not, then increase the module in small steps. For that, refer the standard module series given earlier. Repeat steps D to H till Ft1 is greater than equal to Ft. If Ft1 minus Ft divided by Ft is less than 15%, change B1 to B1 into Ft divided by Ft1. If the center distance is specified, the suggested procedure is select the service vector CS and pressure angle phi. Select material and specify sigma P and sigma G and B1 say 10 to 11. From the given center distance and velocity ratio relation dg divided by dp, calculate dp and dg. Begin with the lowest value of module M, say 0.25 mm. Calculate zp and zg. Steps E to J are as above. For the flow charts, refer reference 1. With this video, the discussion of the gear fundamentals and Spur gear design is over. However, some simplifications have been introduced in the design methodology, basically for the students. Hence, for the final design, the practicing engineers must consult and follow the handbooks and relevant codes. The presented examples of the designs show that there can be alternative solutions for the given problem, and iterations are also involved. Hence, computations are carried out using the computers to get an optimum solution. The notable optimization criteria are cost, compactness, lightweight, etc. The choice of the manufacturing method of the gears depends on the quantity to be produced, material, size, facilities available, etc. Large gears are made by casting, while steel gears can be produced by forging. The gear teeth are given shape by machining for accuracy. For greater details of these aspects, the viewers must consult handbooks and advanced texts. More details can be seen in the reference given here. I hope you have liked the video. Please feel free to send your questions at my email address given on the first page. Please wait for more videos. Thanks.